So today we will be discussing one problem, counting rooms from CSES, and this is problem from the topic grid problem. It is a 2D grid graph problem. So this same question I have copied it in the OneNote. So let's go to the OneNote and have a look at that problem. So first, for solving this problem, we have to know about how we can count connected components in 2D grid. This is something similar to the we count the connected component in graph. Similarly, we will count connected component in the 2D grid also. So in this section, in this part, we are going to learn first we will see the differences between the counting connected components in the graph and the 2D grid, and in the next video we will be solving this counting rooms problem. So first come to the part where we have discussed how to find the connected components inside the graph. So how we are finding the connected component? We are using the DFS for finding the connected component inside the graphs. From the main function, the number of times we are calling the DFS function, that much connected component we are having. So this is our code that looks like, see, from the main function we call the DFS function, then it will see the adjacency list of 1. Since the adjacency list of 1 is not visited, so it will call DFS function DFS of 2. Now it will see the adjacency list of 2. 4 is there, 4 is not visited, so it will call DFS of 4. Now 4 will see the adjacency list, its adjacency list, but since in its adjacency list only 2 is there and 2 is already visited, so it has nothing to do. It will track back. So it track back, and after that the remaining adjacency list will be traversed by 2. So the remaining is adjacency list, in the adjacency list of 2 remaining is 5, which is not visited, so it will call a DFS of 5. Now 5 will see its adjacency list. Since in the adjacency list of 5 only 2 is there, but 2 is already visited, so there is nothing left with the 5, so track back. 5 will track back. Now 2 adjacency list of 2 has already been completed. It will also track back to 1. Adjacency list of 1, it will see 2 is already visited, 3 is there, so it will call it DFS of 3. Now 3 will see its adjacency list. 1 is there only in the adjacency list and it is already visited, so it is going to do nothing from here, and it will track back. Now 1 will again see its adjacency list, and no any node is there which is not visited. 2 and 3 already visited in the adjacency list of 1. There is nothing any node left, so this function is completed and it will return to the main function. Now in the main function we will be seeing whichever node is not visited, that DFS call we will make it from the main function. So DFS of we will use one for loop inside the main function, inside the main part, for checking the whichever node is not visited, that DFS call we will make. So it will check 1, it is already visited, 2 it is already visited, 4 is it all, 5, 3 already visited. So when it will check 6, since 6 is not visited, so it will call a DFS of 6. Now it is visited in the DFS function. It will see the adjacency list of 6, and 7 is in its adjacency list and it is not visited, so DFS of 7 will be called. And in the DFS of 7, no any adjacency list are there which is not yet visited, so it will track back. Now the work of 6 is completed, no any adjacency list left with 6, so it will again return to the main function. So this was for the second time we were calling from the main function. Now we will check in the main function whichever node is not visited. 8 is not visited, so we are calling the DFS from the main function third time. So the count will be 3, and since there is no node is there, so DFS will return to the main. This is how the count is going to be 3, and this will be our answer since the number of connected component is 3 only. Okay, see the code here, you can see the code. The DFS function root is there, we visit that root and we will see its adjacency list. These are the thing for adjacency list, this much, and check if it is not visited, then we call the DFS function, DFS call from here, and it will recursively it will go on. So this is how we were calculating the counting number of component in graph. But how we are going to count in the 2D grid? Suppose we are given this type of grid. This is 5x8 matrix, and inside that we are given some characters. Suppose we have 2 characters, hash and dot, and we have to count. Dot represent the rooms and hash represent the suppose walls, and we have to count the number of rooms. Suppose basically we have to count the number of connected components. So how many number of connected components are there? We are asked means how many dots are there which are connected. So these 2 dots are connected, so this is one connected component. See, this is I'm marking it, this is one connected component. Now we will call a DFS function to here, and it will see in the corresponding edges. We will see what the edges in the 2D grid is there. It will see the corresponding edges. So we see what the edges in the edges in the 2D grid will be defined in the question only. Here you can see what the edges are. You can walk left, right, up and down through the floor squares. Okay, here it is defined that you can, if you are on the floor, then you can walk left, right, up and down through the floor square. Means you are given the edges. What are the edges can be? If you are present at any square or floor, then in which direction you can traverse for, or you can search for the connected component. This is what we defined in the question only. So here you can move left, top, right, and bottom. Okay. So in the DFS call, first we will make a DFS call from here. When we will see the dot, we will call a DFS function from here. It will check at the top. It will check at the left whether it is a dot, no. Whether it bottom, no. It in the right side of it, whether it is a dot, yes, it is dot here, and it is not yet visited. So we will make a DFS call from here, and it will also check in the same way at the top, left, right, and bottom, and it will not get any dot which are not yet visited. Means that function is over, and we will return to the main function in the same way we are doing in the graph. Okay, so this will be visited. Now in the main function we will be traversing the array, whichever array is whichever indexes are not visited, we will call a DFS function from here. So we will check here, this will be these are not visited. So whenever we will call a DFS function main from the main here, then it will traverse all the this indexes, all the dots, since all are connected, this will be traversed. Similarly we will check in the main function, and this all will be traversed. So answer is going to be 3, which is the required answer. Okay, so just see the code and you will be able to understand it better what we were doing. We have used a grid vector, suppose matrix. In this we are storing these characters, hash and the input characters, hash and dot, where the hash and dot are there. And in the visited array we are storing the whichever indexes are visited arrays. No, both are matrices are there, and dx array is there and dy arrays is there. What dx and dy is there? See, I'm explaining it what dx and dy is there. Okay, see, I'm just copying it for now. This I'm copying it, and I will be explaining what dx and dy is. See, if you are at suppose any node x and y, this is the node x comma y, x comma y, this is the node. Okay, and you in the question already said you can traverse in the top, bottom, left and right. So how you are going to traverse that? This is the shortcut. Either you write the conditions, 4 conditions, that if you go for this node, this will be what? X minus 1 comma y. What is the quadrant of this? X minus 1 comma y. What is the quadrant of this? X comma y minus 1, right? What is the quadrant of this? X plus 1 comma y. What is the quadrant of this? X comma y plus 1. Okay, so these are the quadrants that you have. Okay, so what are the things that we are adding? For left, what we were adding in x? 0. For left, what we were adding in y? Minus 1. See here, minus 1 we were adding. For top, what we were adding in x? Minus 1. And what we were adding in y? 0. See, x minus 1 comma y. For the right, what we were adding in x? 0. And for y, what we were adding in y? 1. So see, x comma y plus 1. Similarly for the down, what we were adding in x? 1. 1 is there. And what we were adding in y? 0. So whenever we will be when we will want to traverse the all the possible direction, then we can use that array using for loop, adding each time the possible indexes. So these are the things for dx and dy is there. Int name and count will be counting the number of what number of connected component. N and m is the number of rows and columns. IsValid function is there. What the isValid function is returned? Suppose isValid function will return, suppose you are here at this node. Okay, at this node you are here and you want to check at the top, because at each node we have to check left, right, top and bottom, and you want to check top. But in the top, nothing, no any indexes, no any valid indexes are there. So in isValid function will check whether the indexes are valid or whether it is a dot or not. So it is going to check 2 things, whether the indexes are valid, and the second thing will be whether it is a dot or not. Okay, so this is the isValid function. Raw must be, if raw is less than these are invalid indexes, raw less than 1, raw greater than n, column is less than 1, column is greater than 1. These are the invalid indexes. So we will return what? False, that these are not the valid indexes. And similarly we are going to check that whether the element, the character we want to traverse is whether hash or dot. So grid RC hash, then it is invalid because we want dot to be traversed. So this is invalid. If both the things are not there, both the invalid condition are checked, and it is not there, means this is valid, so we will return true. This is the simple is valid function. And what the DFS function was doing, I'm explaining it. See, in the same way, what we were doing in the graph, first we visit that node or index, you say, and after that we were traversing the connected component or the connected edges of that node. So here we will be traversing the connected indexes of that index. Okay, means we will be traversing the left, right, bottom and down of any particular index. We are given R and C, and we will be seeing the bottom, left, top and down. Okay, so for that we have used a for loop, and new x is equal to r plus dx of k and dy of k. Each time k is equal to 0, then k is equal to 1, then k is equal to 3 and 2. So dx dy, all the four sides it will be traversed using the for loop, and we will check if visited that index left, right, top and bottom, and also it should be valid. If both are true, then we will call a DFS of that index in the similar fashion as we are doing in the graph. If it is not visited, then we are calling the DFS call. Same here also. In the main function, we are taking the input of rows and columns, and we are taking the input of what? The grid, the characters array, character what? Matrices, and we are making visited of all to be 0. And in this part, what we are doing? In this part, we are checking if any node is not visited. If any index is not visited, then we are calling a DFS from the main function. And the number of times we are calling this, we are incrementing this count. We are incrementing this count, and this will give the answer. Finally, we are just printing that count value. So this is the method of counting connected component in the graph as well as the 2D grid. Now we can simply solve this problem. We can simply solve this problem. This is nothing but is a simple problem of finding the connected component only. This is the code of that question only. This is the code only of that question. Same code will run for that question. So I don't think there is any good reason to explain this question in the next video. I think this is the same concept only we will be using in this question also. So see this code, just try to understand, and you will understand it is easy and it is same as the connected component in the graph. So hope you have understood. Thank you very much.